Thank you much for coming and investing your time into this activity. So we are in the computational chemistry, like introductory computational chemistry course. With this meeting, we are completing the chapter on Hedrick theory from theory side and practical skills on using gausview and Gaussian for basic level electronic structure calculations. And the general idea is that if instructor mumbles something, it's boring, but if you see any instructions from your class members, you remember it much better. And another idea is that one cannot learn everything perfectly, but one can get mastership in specific skill and then share with others history of failures and success, so that the rest repeat success and avoids failures. So if so here is the list of subjects and presenters. So they are arranged from basic ways how to they combine launching software and analyzing, looking on different observables that you may need to characterize molecules and materials in your real research work. And it goes for more and more visual as we go down to the table. If you never saw Microsoft Windows, then it is here. If you if you have never seen PowerPoint, it is also here, and all talks are labeled. They're placed on this desktop, and they're organized in space and in names. So 1, 2, 3, 4, 5, 5A, 5B, just because it was last minute change of the order. And there are also names. Primarily first, some of them are last, so just double click, right? Yes?
And you have the most updated version of them?
I hope so.
Okay.
If you do not see right version, do not panic and mumble something, because if you will start re-uploading the versions, we will be killed here. Just it will take too long time. Use your charismatic approach. So double click on presentation, it will pop up, and then there is a little symbol here that will launch this presentation. So with and here is the advancer with laser pointer at this point. Right. This one, this top of the button is laser pointer. Left, right for going forward, backwards to the slides. If you fear that your voice is not strong enough, you can mount a microphone or talk louder. It is here. And with this, let me invite to the stage Hannes, who will tell us any options about
Yeah. So yeah.
And if you like to be recorded, then see if you see yourself. If you want to avoid, if you hesitate, you can just.
I'll be good here.
Yeah. Go away. Please start.
Yeah. So today my topic is the electronic structure. Many of you have good idea about electronic structure. So if you have some great questions, we can always try to answer with the help of symmetry. So what information we will get from the electronic structure, that's important. So this is very self-explanatory slide. We can calculate a bunch of information from the electronic structure, including the total energy, entropy of the system, and the Cusack properties. Its hydration energy, refractivity, polarizability, and we can also calculate the electronic properties like the HOMO, and the vibrational spectrum. These are the some of the properties we can calculate from the electronic properties, but there are many. But because of the limited space, I just put only few. The reference which I used is which is hidden by the screen. The reference when I try to use the the Hypercom software, the semi-empirical electronic structure help me to calculate these properties. So if you really look the list of different electronic properties, we could see a distribution, different types of electronic property, starting from the molecular mechanics.
Keep going.
Yeah, so starting from the molecular mechanics, semi-empirical, HF, Hedrick, DFT, and two perturbation theory based one, and CCAST and BD, which I have no idea, but this all can be found in the tab on the method.
Approach the keyboard and type escape.
Yeah, so Dimitri has given a good lecture about the Hedrick method during last lectures. It's basically an approximation for determination of the wave function and energy of the quantum system in stationary state, means in the time independent state. So the objective of the HF system is to solve the Schrodinger equation, assuming the Biot-Born-Oppenheimer approximation. So wave function of the system can be solved by using the single slider determinant. So single slider is given by the wave function is equal to the determinant. And this is another electronic method. It is not a semi-empirical. So it's based on HF formalism, Hedrick formalism. But the beauty of this is that it can go for calculate the large molecules, and the approximation is based on some empirical data also. And due to ignoring the electron repulsion, the calculation is a bit faster here. And different subdivision of this semi-empirical is AM1, RM1, PM1 methods. This again I have taken with the reference of from the Hypercom software. And this is another electronic method. I think the next coming session we are going to have very detailed discussion on this density functional theory. It's unlike the other two HF and semi-empirical. This is based on electron density method. And here electron density again is a function of space and time, and it's a very fast calculation because only the three Cartesian system is being included. The beauty of this DFT is that it can predict a spectrum of properties, including the molecular structures, vibrational frequencies, ionization energy, etc., which I think we're going to have a very detailed discussion in the coming classes. So how to calculate the electronic structure in a Gaussian? That's the important part of the discussion today. So if you open the Gaussian software, go to the calculate tab there. On clicking on that, it will take us to the method, and again clicking on the method, it will pop up another tab which lists many electronic structures starting from semi-empirical, mechanical, DFT, etc. So we can choose the required electronic structures from the this list of list of electronic structures. So this is another arrangement of precision versus the cost arrangement of different electronic structures. The best electronic structure is one listed. It is perturbation based one in terms of precision, and same time MP2 the perturbation of MP2 based electronic structure is cost is high, so it's listed on the best and the least. Thereby I'm winding up my small presentation. Thank you.
Okay, but thank Anas. Any questions? Meade was first. Sorry.
So when we have DFT versus Hartree-Fock, do you know if those methods would give us different electronic and physical values? Like on the first slide, you showed us those different values that we could get. So would they change much?
I have to get the help of geometry. So DFT,
I was sleeping. You need to repeat the question.
For DFT and Hartree-Fock, if you were to use either one, would you get different electronic values and physical values, things that he showed in the first slide?
Yes.
So they would be.
The band gap computed by Hartree-Fock is about 2 times bigger.
And is that still referring to both physical and electronic properties? Or?
Band gap corresponds to the color of the material. So whatever is red with Hartree-Fock will appear blue. Make sense?
Would that be the only noticeable difference that we know of?
Orbitals would be more localized in Hartree-Fock and more spread over in DFT.
What is QSAR?
Yeah, QSAR is.
Yeah, what is that?
Yeah,
Show us the-
yeah, QSAR. I think I show in the.
We haven't talked about that in class.
Yeah,
What is
yeah.
QSAR?
So basically, it's quantitative structure and activity relationship properties. It's basically the same modeling what we do in the Russell lab. It's basically a software which helps to calculate the molecular data into some mathematical information.
Okay, is
Yeah.
this like molecular dynamics or is this quantum theory?
Not dynamic. It's a molecular descriptor basically.
Just a descriptor.
Yeah.
Okay. And log P is some sort of mathematical way. Okay.
Yeah.
Thank you.
Yeah.
More questions? More questions one? More questions? More questions three?
Thank you.
If there are no questions, let's thank Anas once again. And the next presenter is Benjamin Geffre, who will enlighten our understanding about the basis set that we all have seen when we are trying to do any setup of calculations with gausview. There is a choice of basis set. So what it is, how to deal with it.
Hello, so we're going to be talking about basis sets, and as with most of the subjects in this class, you could probably do a thesis paper on it, but this is no thesis paper. This is going to be a 3 to 5 minute presentation. So, what is a basis set? You know, generally a basis set is simply a set of vectors that span a space, or that can be used to define any space. But for us, basis sets are sets of single electron functions that are used to build molecular orbitals. In other words, we use linear combinations of atomic orbitals to create our molecular orbitals. And there's a few different ways that we can approach this. So we can use these things called Slater type orbitals. We could use Gaussian type orbitals, or we can use contracted Gaussian type orbitals. So looking at the difference, because the equations aren't the important part, it's the shape. So comparing these Slater and Gaussian, Slater is very pointed and peaked. This better represents actual electron density around a charge compared to the Gaussian, which is flatter on top, which is a problem because we want to use Gaussian, because Gaussian is a lot easier to use and a lot easier to do mass with than Slater type orbitals, which is where the third type, contracted Gaussian type orbitals, come into play, and that covers it up. It's on your little sheet of paper, but essentially we use 2 or more Gaussian orbitals to create a Slater-like orbital, to make it somewhat more pointed. So there's a few different nomenclatures, and I can't cover all of them, but we'll cover 3 of the more significant ones. There's the minimal basis sets, which are single basis function used for each orbital. That is, that we approximate every single orbital using one equation. The most common type are the STONG, where this n here is some number. And what this means is, well, we go back here, this is actually our contracted Gaussian type orbitals, where this n indicates how many Gaussian functions we are adding together to create that Slater type orbital, with STO meaning Slater type orbital. There's the Pople basis sets, which have NMLG nomenclature. Each of these NML, those are different numbers indicating different minimal basis sets that are used individually and applied individually to the inner orbitals, small valence, and large valence orbitals. For example, 631G, for example, the inner orbitals would use 6 Gaussian functions for their Slater type orbital. The smaller valence orbitals would use 3, and the larger valence orbitals would use 1. And then thirdly, we have the correlation consistent basis sets, CCPVXZ, where X can be D, T, Q, 5, 6. This is correlation consistent polarized valence X zeta. And X zeta is something that I neglected to mention earlier. It's basically, your zeta is, if I understood it correctly, is how many terms you actually have. Like how many basis functions you actually use for any particular orbital. So this D would be double, T would be triple, Q would be quadruple, 5, 6, etc. And so taking a look at actually how we use this in Gaussian, here's a list of all the basis sets that Gaussian 16 can accept. Do we actually have Gaussian 16 or Gaussian 9?
Gaussian on CCAST there is 16.
Okay. Well, on like what we use.
We use 9.
Okay. So it's mostly applicable. So we have your minimal basis sets up here. We have your CCs. We also have LANL 2DZ, which stands for Los Alamos National Laboratory double zeta. And then this is, what each of the basis functions is valid for. And that's it.
Okay, that's fine, better. Oh, Meade is first again.
Okay. When it comes to those basis sets, are you saying you use 3 to create like a Cartesian coordinate system, or?
They specifically said that they're non-orthogonal vectors.
Okay.
And so you don't use orthogonal vectors, you don't use your unit vectors, you use different ones.
Okay.
So the basis vectors we're using in this case are atomic orbitals.
Yes.
So you use like Slater type orbitals for when electron is close to the nucleus, but then when it gets further out, you use Gaussian.
Those Slater and Gaussian are, I kind of regret putting these transitions in, but Slater and Gaussian are two different ways of approximating the atomic orbitals that we are going to use to approximate our molecular orbitals. So we don't like actively change them, or at least not in this case. I'm sure that if you wanted to, you could create a basis function that actively changes what type of orbital we use as we get further out. I'm sure someone has thought of that, but we don't do that, or at least not for any of these.
So just to clarify, the basis sets we're using in this class are just atomic orbitals or molecular orbitals?
The basis sets use linear combinations of atomic orbitals to create the molecular orbitals.
Okay.
More questions? Oh, okay.
Why is the Gaussian type preferred?
Because of this square, this r squared here. Well, I think I forgot a negative sign. Yeah, I forgot a negative sign. So if we were to integrate.
Or you may tell that your alpha is negative.
Yes. Oh, yes. My alpha is negative in this case, which is important. So if we were to like integrate these two functions, if we were to try to take the integral of e to the negative r compared to the integral of e to the negative r squared, e to the negative r squared, that's a very well-known integral. Meanwhile, you can't actually take the integral directly of e to the negative r.
Makes sense? Okay.
What's the little n in ours of that?
This is an index that corresponds to some quantum number. I don't remember which one.
What would be the n for s orbital?
1.
Okay, so you get pure exponential.
Yes.
What would be the value of n for p orbital?
That would be 2.
Okay, and then you do power, first power, r times exponential. That will reproduce p orbitals. Make sense? More questions? If no, let's thank Ben once again. And guess who is the next presenter? Gage. Huh? Yeah. So Gage will present on available tasks. So it is practically important question for modeling properties of molecular materials. And we are just 2 minutes behind the hard deadline.
Uh-oh.
Don't worry, I'll fix that.
Oh, thank you.
Okay, so basically just a continuation of my last presentation on what you can do in GaussView. So for starters, everything that I do here revolves around opening a calculation menu for this. So just right-click, calculate, Gaussian, so the first job type we're looking at is energy, which it defaults to, so that's nice and easy. So you just run that job, and you open up the results window, go to summary. What it does, it'll open up this little window here, which might kind of be hard to see on here and on paper, but it gives the file name type, how it was calculated here, which would be the single point energy, basis that we use, it gives the energy of, it says negative 229 atomic units. Here's my last presentation. I have the corrupted benzene model. I went to optimize it this time, and it's now fixed. Frequency, which gives us a few things here. Again, frequency opening up the menu. And again, you right-click and open it up. Vibrations will only show up if you do the frequency calculations. You have to do the frequency calculations for it to show up. It could show up, I guess. And we don't care about those numbers right now. I'll get to those in a second. So you can actually show how it vibrates by starting the animation, but because I can't really show that in the PowerPoint, I also turn on the displacement vector so you can see where it's moving. Not terribly well on this one, but you can see the arrows here, so that shows how it's kind of moving. There you go. Just pretend it's smoother. Now back to the numbers I said to ignore. So we can open up the IR spectrum here, which I have kind of blown up a bit. And if you notice the peak right here, you look back on the numbers, where the IR shoots up is at 784, which is right about where that is on the spectrum. You kind of see another one here at about 1136. That's the little one. And the other one should be showing up. I just didn't really want to scroll that far. And it actually gives you a few more spectra than just IR. So you have Raman, and P and U depolarization. That's what I got.
Okay, let's engage. Questions? Meade, you're the champion of questions.
Do you know if that spectrum was the same thing that he showed? Was this spectrum? Do you know if that's calculated just with different solid?
I didn't understood the question. Maybe the speaker did.
My apologies. Yeah, it's kind of, I'm sent it to him, but I know Anash showed a spectrum thing earlier. Do you know if that's the same thing between what you showed and what he showed? Because that would be two different programs, obviously calculating the same thing. I was just wondering.
I mean, theory.
Okay.
I have to look at
No, different.
Different. Okay. Yeah, I have to look at that one again.
Yeah, no worries. Yeah.
More questions? So, definition, what is normal mode?
I thought that was in a later presentation.
Huh?
I thought that was in a later presentation.
But you are already computing them. You may try your best.
I may have been accidentally computing them.
Yeah, but you were even visualizing them.
Oh, we're talking about the vibrations, aren't we?
Yes, yes.
Thank you.
You're welcome.
You know, there is a contest, competition, Dance Your PhD. And you get prize and free ticket to Australia.
Do it. I'm gonna do it.
So what is normal mode?
How it vibrates? Rather.
But why there are many normal modes? Why you show a list of them?
Well, there are different ways the molecule can vibrate, like back and forth, side to side, you know, like that.
And why they have different frequencies?
The bonds respond to different frequencies. Usually
Okay, good. It's a good starting point, yes. Yes. More questions to Gage? You do not need to answer if you are not comfortable, but try. Your normal modes show list is so long, with like 10, 20, 100, and your infrared spectrum has maybe like 4 peaks for your mode. Why not every normal mode contributes to infrared spectrum?
Simply because at most points it's not really responding to that, it's only picking up at a few of these points here. At that point it's barely picking up to the point where if it wasn't surrounded by zeros, I'd be inclined to ignore it.
But just your vision, what is responsible for one or another type of molecular motion? What is responsible for contributing or not contributing to interaction with light, with absorbing or emitting infrared radiation?
Spins?
Huh? No, but you can answer.
I think
Transition. Right?
Not enough.
Okay.
we do it.
So what is the Hamiltonian of interaction between light and matter? you do.
Wait, can you repeat the question?
What is the Hamiltonian of interaction between light and matter?
Between light and matter?
Yes, between electric field and any material object.
The gradient squared plus
Simple. Simple. Much simpler. Electric field strength E times
Q.
if it is charged system, and if system is neutral,
Oh, it's a 0.
no. It's a little puzzle. We will need it later in the course. Sorry for stopping us from this glorious journey. So if your molecule is neutral and you irradiate it with light, it still may respond, right? Because we have so many neutral molecules, even infrared frequency. So your motions of molecule create imbalance of charge, so that from the bird's view, it's neutral. But some portions of molecule have delta plus, some delta minus, and they form dipole. Electric dipole. So those bending with distortions that create dipole will respond to electric field.
Does that have something to do with depolarization linkages?
It is related. It is not directly, but it is related.
Okay.
Make sense?
Yeah.
A small value less than 1.
So, okay, if Q plus
Partial.
is the charge, what is it when it's neutral then?
Huh?
If Q is for charge, right, we didn't answer what it was for what
No,
it's.
if you have like hydrogen atom,
Yeah.
you have +1 for nuclei and -1 for electron.
Mhm.
But there could be dipole.
Okay.
Okay?
We don't need an external system to orientate the dipole,
Electric field. Yes. But probably we are done with questions to Gage. More questions to Gage? If not, then thank you once again.
Also, thank you for answering the question. Let's see here. Okay. All right, everybody. Today I'm going to be talking about normal modes, scan and reaction coordinates, and transition state search within Gaussian 09. Okay, cool. All right. So what we have here is there's some pretty famous kind of, interesting studies. They're very hard to study. I got this guy to work, whether he's representative or not, we'll get there. So if you take methane, this is not methane, but if you take methane, you interact with oxygen, you might get some type of combustion reaction. So we'll see if we can get that here. This is the closest thing I got to
Just what's the name of this compound?
That would just be alcohol.
David Graupner. So I'm not asking you for a second because I'm confident in you. Anyone else? Yes. So it's and what will be the name if it will be CH2 group between this red oxygen and CH3 group?
Methane?
No. If there will be right now it is CH3OH, and what it will be if it is C2H5OH? Yes, which is like right. So and this is toxic. Although some people consider it as a substituent, but it won't get complaint after.
Yeah, don't drink it. So, okay. So, I got this guy to work. Yes, because it took me forever. But so what we go ahead and do is, this guy's already optimized here. So I can open this up in a separate file. Open this guy up, hit scan. And then we want to make sure that the redundant coordinates are relaxed. Pay attention to your little message at the bottom, because we need to fix our redundant coordinate, or go to our redundant coordinate editor. So next step is open, while everything's open, just go to your edit, go down to here, And then you'll still have your molecule open, and you're going to select add. So then you go down to this area, you'll have some options, click down here, hit bond, and then you need to actually literally select the bond. So 1 would be corresponding to 6, for example, and 2 would be 5. Then this is where you need to play around because it can do weird things. I just decided to take a low amount of steps because it actually worked. When I did more steps, it wouldn't converge. So I just decided to go low, and it worked. Let's see here. Whoop. Yeah. Okay, we'll go back. So this is from when you optimize successfully, you get the file and you open it, or you look in the gausview and you can pull down the scan. You click it, and it produces this chart. And so you have the scan of total energy, and you have the scan. I'm not sure what RMS stands for, but this is the gradient norm. So
Anyone?
root mean squared? That's what, okay. So this is the options you have to produce this graph. It's nothing too shocking. You know, it gets down to this energy.
Wait,
Go back.
why is your graph different from what I have on the paper?
On yours? Oh, I'm sorry, because I had trouble optimizing and I was given a small extension. So yes, when you see on the paper is not correct.
Okay.
This is my most updated one. So
Because I was not able to print, like after it is went for printing, it was too late.
Yeah.
Okay.
So if you actually want a copy of this, we can print copies up and give it to you. So this is the correct way to do it, and you should get something like that. It's still right. It's just for this guy is like more right because it's the correct one. When you're done producing that scan, you can now go to your out file of your previous run, make an input file, and you want to save your normal modes and perform a frequency calculation. So what that involves is, you know, the usual name your check file, frequency, save normal modes. Do your unrestricted, because that's just much nicer. No sim. You know, give it a title. I just didn't give it a title here. So what that does is, as shown earlier by Gage? Okay. We had this nice table here of all our frequencies. Only difference is we have a negative frequency here. That's important because that suggests a transition state. Problem, now the thing you gotta keep in mind is this is a very tiny system and I'm only dealing with the oxygen and attaching to, you know, my carbon. You could have something way more complicated and you'd have several of these. Which one is the right transition, you don't know. This is a simple case. We'll see what it gives us. So here we go. And this is a and so here's my run for my money. I don't know. Oh, why did it stop? Was it that? Oh, it's a really quick movie. Wow. Okay, so as you can tell, it goes back and forth. So this is the frequency of motion. These guys move very little, but they do move. This one is the big one though. That's where we see that negative value. Now, there is one last thing I need to tell you. If we go, oh, that's cool. I can actually do that. Okay, all right, sorry. Can we go back? Hello. Okay, here we go. So when you are in this position where you have more than one negative frequency, all you have to do is go back here and type in, you put a TS in there. So you put a transition state. And that would find your true transition state. And there may be another keyword in there, but that's how you would do it in that case. Any questions?
Okay, let's thank the speaker for the presentation and paper is open for discussion. Me? No question.
Give me some time.
Oh, okay.
Here, I'll just play the video.
Can you back?
Oh.
So how Stop.
Okay.
So the top curve, how do we call this curve in the course?
I would call this our
Especially in the first chapter of the course.
our hump that we have to go over.
Huh?
Our hump, our reaction.
Three letter abbreviation.
Letter abbreviation.
Uh-huh.
What does it start with?
DOS.
Yes.
Didn't see it starts.
Yeah. Thanks. Ready to kill. Potential energy surface. Oh, now we have ripened
Okay.
wave of questions.
Sorry, that thing that you showed us, the transition, you're saying is that relating to these graphs, or kind of like that video you showed?
This is the vibration, right?
But that
No, it is a scan of a coordinate.
I'm sorry. These are the scan of the coordinates. Sorry. What I showed you here was the vibration.
So none of the information before showed us the vibration. Okay.
Yeah, sorry.
No, it's okay.
Also, too, what you notice here is there's just one. You could have several different vectors, and you have to use that transition
Yeah,
stage
it's just no, like,
search.
went- Went back and forth.
Yeah. So
graph
sorry,
would
this
go
just
in.
scans the coordinates here, the total energy. Just drives the total energy. Yeah. Okay. So if you were to plot this on a nice presentation for a publication, this would be just not choppy. You'd have more points in between. You'd have something with a nice curve.
More questions? I see. Thank you. So for transition state, should it be negative frequency or imaginary frequency, and why?
It should be negative.
Any other opinions?
How would I know if it was imaginary? Because I just remember.
So suppose you do scan of your potential energy surface, and you would get image like this. Right? So you position, and here you would get for your motion you have mass, and you have Hooke's law constant. Right? What will be the frequency? Anyone is free to help.
Isn't it just like a product, or?
Like if you have mass and the rigidity of the spring,
Is
how
it just
you-
mass times the?
the heavier mass will slow down the frequency. So it will be maybe the ratio.
Root K by N.
Huh?
Root K by N.
Root
K
of
by N.
and it should be a factor like 2 pi or whatever, right? Okay, what is K?
Stiffness.
Yes, but mathematically, if you have potential U of R,
Wait, number?
like you have potential energy surface, you found a minimum. How to find rigidity constant?
Secondary. Secondary.
Right? So if you are in the minimum, what is the sign of second derivative? Positive. So in minimum, K is bigger than 0. So in both here you have dr equals 0, but here in the maximum you also have dr 0. Right? What's the difference in these 2 points?
Sign of K.
Okay. So if you plug in of negative number, what's the square root of -1? Huh?
Root 9.
Square root of -1? Hi. Imaginary unit. So it should be imaginary frequency. So if you are seeing that your normal modes include imaginary frequencies, it means that you are not in the minimum but in another extreme of transition state.
Okay. So,
Okay? So
this
it's
is
a backwards logic.
Okay, so this is a
Right?
transition.
This is forward logic, and there you see backwards logic. As soon as you see imaginary frequency, it means you found transition state.
Okay. Okay. But question. Wait. I have a question.
Yes.
How, so this. Are you saying this is not the most stable
What?
transition state, or just a transition?
A transition state.
A transition state. Okay.
More questions to Marymal. Questions 1, questions 2, questions 3.
All right. Go ahead.
Thank you so much. And Nathan will continue as a rabbit and will bring us from colorful universe of mouse-operated gausview to solid.
Can I ask a question? What's the name of class?
Mass.
So we use
Yes,
okay.
yes. And if there, since there are many atoms, it's like reduced mass.
Okay.
All right. so far in this class, when we've used Gaussian, we've been using the photon computer, and that has graphics forwarding. So what you can just do is type in gview.exe and then use a GUI interface without a care in the world. But there are some computers out there that doesn't have graphical forwarding, so you have to make do without a GUI interface. So I'm going to walk you through the process of how to use it without a GUI. Okay, so you'll need some sort of starting input. I decided to start with an XYZ file because XYZ you can read with JMOL, and JMOL's free, so anyone should be able to use it. So the first thing you'll need to do is convert that XYZ file to a input file for Gaussian, the com file. So we've done this before with Babel, but I thought I'd just remind you guys. You have the Babel command, you have the -I for input, XYZ for the XYZ input file, the name of the file you're going to convert, and then -O com, and then the name of the file you want it to convert to. And then like before, you'll have the result, just a list of coordinates with some stuff up top that's specific to Gaussian, but still there's a problem. With any calculation you want to run with Gaussian, you'll need to specify some information, and the file I just showed you on the previous slide doesn't have that. So you'll need to figure out what to put in that header up top of the file. For that, on the photon computer in the file bin, so to get there just type ~bin. There's going to be a file called header_HF. That's just a template header for the Hartree-Fock functional for a Gaussian file. I have a picture of it just right here. All this stuff is what you're going to have to edit, but I'll show you how to do that later. For now, I'm just going to show you how to take this header and put it into the file you just created previously. To do that, there's a command in Linux called cat. It just takes two files and puts them together.
What's the connection between this command and animal?
Very little. It's short for a concatenation. So if you just look at the command cat, that just tells you want to use that process of taking two files and putting them together. And then the first thing after that, you want the first file. That's important because the order matters. If you switch head_HF, which is this header, and the example, which is the coordinates around, you'll get the coordinates up top and the header out on the bottom, and that's not really what you want out of a header. So just get the order right. And then you have this right forward, this caret facing to the right. That just tells you that you want to put these two files together and put an output. And then to the right of the caret is what you want to call the output. So if you do all that, you should have something like this. It's the file from before, but this time it has the header up top. From here, you just need to make sense of what's up here in the header and how to edit that to get what you want out of it. The first line, it just specifies the check file. So that's one of the output files you get when you run a job. It just, you tell it what to call it, and then after the job's finished, it'll put that check file in the directory. The next two lines, memory and processors, that just sets how many resources you want for a given job. So in this class, we haven't really done any of that, or at least I haven't. But personally, when I've used in my research on VASP, I've actually had to care about that, specifically the number of processors. If I used more than one, a job would crash just like 10 minutes in, so I had to actually manually change that. So all you really have to do is just change the number. If you want to change it to one processor, just put one. It's pretty easy. And then the next line, this hashtag P, that tells Gaussian that you want some extra output. The HF, that stands for Hartree-Fock. If you want to use something else, you'll have to look up the tag and put that in there. As a disclaimer, I don't really know what all the tags are. There's a bunch of them. You'll have to look them up anytime you want to use it. And then right after HF, there's the dash lanl2dz. That's just the basis set you want to use. Again, there's tags for all different sorts of basis sets. So just figure out what the tag is for the one you want to use and put it in there. And next is nosim. So what I was able to find is that Gaussian, if you enable symmetry, it'll like change the coordinate system of your structure throughout the calculation, and just putting nosim doesn't let it do that. It keeps the same coordinate system throughout. And then there's this cache size. That's more resources, but I really, even outside of this class, I've never had to worry about the cache of something. But if you do need to change it, just change the number. And then down here, 0, 1, that specifies the charge and multiplicity. So with this one, there's 0 charge and it's in a singlet state. That's what the 1 is for. If it was a doublet, it'd be a 2. So, and then once you have that, it should be good to go. And to submit it, you just want to type G09 for Gaussian 9 and then the name of the input file. And then after it's finished computing, just type ls-lt and you can see the files that it put out for you up top. But that's all I have.
Okay, that's done. Thank you. There is a line.
Yes.
Is there any criteria you have to follow for like the spacing at the bottom?
Spacing at the bottom. I think I read somewhere that there has to be like 3 hard spaces at the bottom, but I never tried it without it, so I can't confirm that it's needed.
Did it work for you without putting spacing at the bottom?
I didn't try it without putting spacing. So, but I've heard that there is a problem. I just can't confirm it.
More questions? If no, let's thank Nathan once again. So, Kurt, we will continue the story. What to do if we do have only command line text connection and no graphics on one hand, and if we have high performance production on another.
Alrighty, I'll try to muddle my way through operating Gaussian on CCAST. CCAST is the Center for Computationally Assisted Science and Technology. to obtain access to the CCAS server, you'll need to go to that website link there, and they have a nice little form where you'll need to enter your name, your email, a sponsor, and then the actual software you want to use. So correct me if I'm wrong, we just have CCAS 9 on there, or do they have 16 on there, or Gaussian 9 on there? They have 16 on there? Okay. How this kind of differs from normal computing. So if your personal computer is like a Toyota Corolla, it was engineered with a user-oriented design. It's designed to be easy to use. Everything should be fairly intuitive. Photon would be more like a race car, and then when we get into the actual high-performance computing, now we're getting into like rocket cars. Things that go wrong can go wrong very, very fast, and they can lead to a lot of complications and leads to lots of headaches for system administrators and yourself. So if you are using these systems and you need help, make sure you can contact the support. They're at support@ccast.adc.edu. So the batch scripting is done with an open source variant of the PBS software. PBS is a portable batch system. All your commands will be PBS in the actual script file itself, if I remember correctly. One of the advantages of this is it can email you when your job starts, when your job's completed, and if it errors out. So you can also specify the input, the output file locations, and specify what kind of resources you'd like to have utilized for the job you're trying to run. Here's an example of a little PBS script. So it has file name, usage. I think I should put that one. Queue name. Nodes. Wall time will be like the physical. So like the clock. Imagine like a clock on a wall. So that'll be how much time you're willing to devote to this project, the amount of RAM you would like to have for this project. Inputs, outputs. Questions. Interactive and non-interactive jobs. So an interactive job, you're going to have the shell open the whole time the job is running. You're going to be able to specify. You might have some. If it's running as a shell, you'll have some interactive abilities, so it might request variables. It's more helpful when you're debugging software. Non-interactive jobs are the ones you submit via the scripts, and from the looks of it, from the way CCAS is set up, it will give you access to more resources than if you're trying to do an interactive job. Monitoring jobs. This XD mod, I've not used it a whole lot. It seems very similar to Zabbix, although it gives you more information on the clusters overall. And if I remember correctly, there is a jobs tab in there. And then there's also a command QStat that I found out about a few minutes ago and with emails, and that can give you information specifically on your jobs.
Are you done?
I believe so.
Okay, let's thank Kurt. Stream of questions from me.
What is a shell?
What
is a shell?
A shell is the user interface you'll have on your local terminal or local computer.
Oh, okay.
It's the command line interface.
More questions? Especially those who run Gaussian and CCAST, please try to torture code.
So if you require more like space to run your program, what should be like
When you say more space, do you mean like more
memory to
like So if I'm
Every
So if you notice here, are we using Thunder or Cluster 3? Or both? Thunder? Okay. Well, it looks like you can, depending upon which execution queue you go into, you can choose the number of cores you have, the number of hours you have. On Thunder, it looks like there's even more delineation as to what resources are available to different types of jobs. So I kind of, I'm not overly familiar with the exact setup of these systems. Yes.
What is the mathematical equation for Gaussian scale up? Like in terms of the time you give for, here's a mathematical equation for that, isn't it?
Big O operations?
It's like,
Alice can answer this. Or Anas can explain why the formulation question is incorrect.
oh. What is, there's like a scale up, like how much memory you can assign something depending on how big your job is. There's like a relationship between the two.
I thought there was just the amount of time you thought it would take, not
No,
specifically.
Gaussian jobs really need memory. There are some individual relations, but it differs substantially from method to method.
Yeah.
Mhm.
Method and basis set, so it's not the size of the system, but mostly basis set method. Less. Semi-empirical is the cheapest of every structure.
It is?
Yes. Who has an experience of running Gaussian and CCAST? Okay, who has not? You know, 1, 2, 3, 4, 5, 6. Okay, so question to Kurt, just where to start from if you want to run something on run Gaussian CCAST?
Well, first you need to gain access to it.
Suppose everyone in the class is expected to
have access,
send
okay.
email. You were showing in one of the slides the email. So send email to support that you need an account there. And at least by the time when projects will start, you should have it.
Okay.
What else?
So after we make our account, can we use that example batch script as in a template, you know, to like figure out what code to write to like run Gaussian on CCAST?
Yes.
Okay. Different questions. So who thinks that we cannot and explain why?
Okay, at this, because we run on a batch system.
No. Just administratively, not physically or computationally.
Oh, because of the nodes, because the, oh.
So you need to request this form, sign it and send it back to administrators. If you do not do it, then your account will not see. If you run these batch scripts, they tell, I don't know what you are talking about, we don't have Gaussian for you.
Oh, yeah.
So they manually, you just tell that you are not going to do bad things and they allow you to do it.
Also, before I run that batch script template he has, I have to fill out the form and send it.
Yes, you need to request
Right.
this form, sign it and send it to them.
Right, and when you do the thing, filling out the form, you have to request Gaussian.
Okay.
It's a special, and then they give you the form to sign.
All right.
Yep.
More questions to Kurt?
Or anyone?
No? Okay, well, thank you once again. And before the next presenter will take the stage, I just quickly go through. So after you sign the form, there are examples of batch scripts which are a little longer than those that Kurt was showing general script. And here are, they will be recorded, examples of the
I can share
What?
my batch script.
huh?
I can share my batch.
Please do. And what is important in the script, there should be command model load Gaussian. If you didn't sign the form, it will give you error here. It will not load the module. And there is also a big amount, not here, big amount of the script that deals with distributing your question over several nodes. If you are just doing like methane molecule, you don't need it. Yes?
And you have to run Scratch.
It is included here.
Okay.
It doesn't scratch. And actual command is here, right? So the script will understand that G16 is executing of Gaussian only if you put this command and only if you are included into Gaussian group. So after you have it, so you create your PBS script, you submit it with the command qsub, as Kurt may have mentioned, right? And then after it is submitted, you check whether it is running with qstat command, which Kurt also mentioned. And if you don't care what other people are doing right now, if you're looking only selfish, you just put -u and your username. Otherwise, it will garbage your screen with 3,000 other jobs that have been submitted. And then it shows that some jobs are in the queue status and some jobs are in the running status. Okay? So I don't care for the course and for instruction, but you may care for completion of your project or for later use of Gaussian for your research. So submitting R means good. Okay, and the next presenter will be
Kweeni. Go.
So he's staying on the glorious path of using software without graphical tools.
Well, we've all done this in class, so this will be pretty fast. So, this time. So what I'm gonna be doing is analyze Geo9 output without gausview. Without gausview. Alright. Okay, so yeah. So first of all, just gonna get to the point here from the last lecture that Dimitri taught us about. He did mention that the ionization energy is equals to HOMO, and the electron affinity is equals to LUMO, and also I'll be trying to show like the holo gap and the total energy from this presentation. So, like usual, go to GView. Hey, this is a light stuff I can take. So you go to GView, the DXE, right? You make your compound, and then you exit, and then you process your compound. You use the Geo9 function on your compound, and in my situation, I named my compound coex.com. Oh yeah, and also you also save it as a .com file from the GView, and then you type more just to like see what you've created in your file, and it shows you the Cartesian coordinates so far because you haven't really done much on it. And then you type ls. This is really funny. Anyways, you type ls to find out what files have been made after you use the Geo9 function. And these are other files, but we can see right here the file I made and the new files that were made after using my Geo9 function on my compound. And then you type. So to get your holo energy, your final energy, and your gap energy, you can type this function down, and you also have your compound name from gausview and .log, and here you have 2000 is the number of energy steps you're using, and 10 is it's more like a grid kind of away and above the homo lumo, just like it's explained here. So down from homo 10, up from lumo 10. So that's what it means there. And the width of the Gauss 0.1. That's what it means there. So after you type that and you push enter, and it brings up this information. And from here you can, I feel this is another way you can get your homo lumo energies too, because down here it gives you the homo and it gives you the lumo energy. It also gives you the gap energy as well down there. And it gives you the initial energy of your system and the final energy of your system down there. And then after that, you can type ls again, find out the new files that have been made after this function right here. And yeah, it's just a good way of keeping track of, you know, what files have been made and what files have. So, and then after that, you type more. Okay, so back here, we see that a log file. Okay, we see that a log file wasn't, the E log file isn't made here. And over here, I think I skipped something. Yeah. Okay, so after that, you come over here to the new files that have been made and you type. So this is another way of figuring out the homo lumo by where you have the changes right there, right? So you type more E code the name of your file .log, and then you can get this, your homo lumo in this way, where we have it corresponds to like the last information that was given to us here. Like here we have homo 11 and lumo 3, and here we have homo 11 and lumo 3 just as well. So this is just another way of like figuring out your homo lumo. And then you can do the gap method too, the way you have the gap. So you go more your compound name .log, and this one is quite different from the other one because here I did more E energy compound name .log, and here I just did more compound name .log, and here you use the gaps to like figure out, like Dimitri said in class, you can just count it like, so I have 1, 2, 3, 4, 5, 6, 7, 8, right? And here it goes all the way down to 8 as well, which matches it. So this is another way of figuring out your homo lumo too. And yeah. So also now you can so we want to like copy the files we've made so far from this process to another format, so we can like get like the energy states and get a PDF version like what we did in class. We all did this. So you use this function cp does w01 your compound name log does.log, right? And then I think more files are being created there because of that function. And then you use the gnuplot command to plot your energy states. And after that, you change the format using this function here. And after that, you save it on your desktop, and it saves as a PDF format. And you can get pictures as nice as this one. So, that's it.
That's then Oh, many questions. Kevin? And then Nathan?
Okay, can you go back to that HULUE final E gap E? Back. There we go. So that command on the top there, that actually makes the .log file?
Yes.
Okay, and what does homo lumo mean?
Homo lumo.
Yeah, find homo lumo, like on your next slide. Just after that. Yeah, homo lumo, what does that mean?
Where are you talking about?
Up there, find homo lumo.
Oh, like find the homo lumo. I'm just saying, like, you know, from here, like where you see it changes. That's where you find the homo lumo. Right there. So you have homo lumo. That's all I was just trying to say from here. It's just like a direction for myself to, like, you know, talk about pretty much. So find homo lumo. You come all the way down here where you change. When it goes from negative to a positive, you find. So it's
Can you open the abbreviation what homo and lumo stands for?
So highest occupied. Right?
Oh, molecular orbital.
Yeah.
Okay.
So is that what you wanted?
Can you point to the homo? Okay.
And lumo is lowest occupied
Molecular orbital.
Most unoccupied.
Unoccupied, yeah.
Unoccupied.
Yeah,
So where's that at then?
I can see the question. Occupied or unoccupied by what?
by electrons?
Yes. And your column number 4 in your file that shows 2 or 0. What, 2 or 0 what?
2, I believe that should be
Electron?
yeah, electrons. I
So it's
guess.
not atoms, not orbitals.
Yeah.
Sure.
And
Okay,
when you track down for these 8 orbitals, they all have 2 electrons. Their orbitals are occupied by electrons.
Okay.
And you count until you have it is the last one that is occupied,
Okay.
or highest that is occupied.
Yeah,
And
which
then
is
when
this
you jump
one.
to the next step, it
Is
starts 0, 0, 0. It is
lowest
the
unoccupied.
Lowest unoccupied.
Yeah.
By electrons.
By electrons.
Uh-huh.
Okay. So lowest unoccupied molecular orbitals by electrons. Okay.
Wait, I'm sorry for more questions, but
Alright.
I don't understand what the first 3 columns mean.
Like 1, 2, 3.
Oh, yeah.
I think these are the energies right
Okay.
here, right? I'm not too sure what this one means though, but I do know that this is the energy, and here it's showing the number of electrons.
Okay.
All right.
Well, if you look at the very bottom row, it tells you what the 4 columns are.
Oh.
What? Okay, so you said energy.
Yeah, but what is the A that U abbreviation
It's
there?
a unit.
Atomic units.
Oh, so it's
It's a
okay.
conversion.
Oh, okay.
So what's a factor of conversion between electron volts and atomic units, roughly? What is bigger, electron volt or atomic unit?
Well, apparently electron volts is bigger here.
Uh-huh.
Oh, here.
No. They have like larger numerical value.
But there's
Like, what is?
Oh, you mean like
What is more
conversion?
expensive, 1 cent or $1?
Well, okay, so just going based off this, I could tell that atomic unit is bigger because if you're converting, it becomes smaller. So it means some kind of the division that makes it,
27.
yeah. So
So atomic unit is 27 times more expensive than.
then, so if you multiply this by 27, you get that. Okay. Well, is there more scrutinizing
first
questions? You say?
What? It is a question of Kevin. What is the first pole?
It says the state.
So it's just number of orbitals. You count them.
So yeah, it goes all the way to 8. So 8 orbitals, and then you have 2 electrons in each orbital.
Nathan wanted to ask something.
You already answered it. It was about the units of the energy.
Sorry,
It's nice.
Oh, another.
Yeah, I just want to clarify something real quick. So the highest occupied molecular orbital is the orbital with the highest number of electrons and the highest energy, right?
No. It's not the one with the highest energy.
Okay.
I want you to continue this question. If you look on energies of orbitals, starting
Yeah.
from 1 and going down to the list, what do energies do? Are they growing or decreasing?
They're decreasing. From
But
1.
No, there is a minus sign in front. It starts from like minus 100, and then it goes minus 20, and then it goes to 0.
Are we gonna ignore them?
No.
The energies are getting bigger as you go down the list.
Right?
More negative
Yeah, but-
is smaller, so if it's getting less negative, it's getting bigger.
Oh, okay.
Okay? So as
Alright.
we go from 1 to 10 and further, energies increase.
So we're gonna ignore the magnitude and just go by the signs. Is that what you're saying?
Absolute value, not absolute value, but the take into account the sign.
The sign. Okay.
Like the direction on the number line, if it's to the right, it's bigger, if it's to the left.
Oh, okay. All right.
So as you go further and further onto the list, energy grows.
Okay.
And then you observe simultaneously energy value, which grows, and occupation.
So just as he is just said, it means 8 right here is the highest so far.
Is the highest out of those that are occupied by electrons.
By electrons. Okay. So you were right. Yeah.
But it could be a different state depending on your system.
Yes, but right now, as I interpret the question by Kevin, we are trying to be very strict with verbal definitions, like highest among whom? Among those that are occupied by electrons. More questions to Kweeni?
Scrutinizing
Thank you once again. And the next presentation is by Kevin. So he will tell us a little bit more of how to convert numbers into images, and he kind of revives us and bring back from boring numbers to exciting images, specifically related to density of states.
All right, guys. So this is like density of states. I've designed this presentation to be like really short, just to get the bare bones of what you need, a little reminder of what density of states are, and a little code you can use as a template. Okay, so before I get into the code, let's talk about what is density of states. Density of states is basically a plot showing the number of states, per energy level, or like an energy interval. And this is like an equation like showing the mathematical definition of a density of states. Now, why is density of states relevant? If we remember in quantum mechanics, which is basically like part of what we're studying, energy is quantized and discrete. So in regular classical mechanics, energy can go from like 0.001, and then it gradually like increases or decreases. But in quantum mechanics, energy jumps straight from like one energy level to another. There's like no in between. Now, for those of you who took statistical mechanics, I just want to like throw this like a quick aside. So we've all studied, microstates and macrostates. If you remember from statistical mechanics, the macro state with the highest number of microstates, that's really going to be the most probable macro state, the one that has the most microstates. It's the same idea here for density of states. The reason density of states is important is because basically the energy interval with the highest number of states, that's basically the most probable energy we'll get basically. So that's the basic idea of that. Okay, script for plotting density of states. I've designed this slide for you guys to use as a template. So if you like don't remember anything from about how we plotted density of states, you can just download my slide and just literally like copy this code and use it as a template, and then you'll get your density of state plot. So here in the first two lines, we're bringing up the code needed to make our .log file. This is related to what Kweeni did in the previous presentation. Right here, where my pointer is a .log file we're using. Okay, and then on this third line, we're copying our .log file. We're copying this, and then we're making a new one that's just named dos.log. In this line, we're actually literally making the density of state plot. And then this line here is a conversion. We're basically converting from a PS to a PDF, and we're using this DOS file under that. And then the rest of this code, the last 3 lines, is basically what you do to basically access your density of states plot. You may not necessarily have to use these last 3 lines of code. If you remember on the MOBA Xterm interface on the left-hand side, it shows a bunch of these folders. So if you have a mouse in a graphical interface, you can just click on the new PDF file you made, and it should open it. So yeah, like I said at the beginning, if you don't remember anything about how to plot density of states, just download my slide and just copy this code, and you know, if you follow it, and you may have to make a couple of minor modifications, you'll get a density of state plot. And here's a quick example. Density of states is on the y-axis. Orbital energy is on the x-axis. It's in electron volts, and the states with -20, -15, and 0. They're the most probable because they're the ones with the highest number of states. So this is just a quick example of how we use a density of state plot. And that's the end of my presentation. Thank you.
Okay, thank you. 3 questions. First, this time was Nathan. Second, Mary. Third, then.
On your first slide, you talked about discrete energy levels.
Mm-hmm.
So when you're using a density of states, do you have to consider discrete energy levels, or can you do it continuously?
The density of states plot is always going to be discrete, because we're not using classical mechanics. We're using quantum mechanics, and in quantum mechanics and in quantum chemistry, which is what we're studying, energy is always discrete.
On your last slide, you have a plot of the density of states, and it looks really continuous to me. Like the actual line, there's gaps, but.
All right. Maybe I made a mistake in making that a density of state plot.
No mistakes. No mistakes.
Not actually. You can get the discrete value if you reduce the line width. So as it's a higher line, so it's getting a continuous. It seems like continuous, but it's discrete. So if you reduce the line, then you can find the distance maximum. That's my understanding.
That's good. That's good. And another observation: if when you go from smaller system to larger system, there is a trend. The larger the system, the larger number of electrons, larger number of states, and higher the more continuous density is. Right.
Mm-hmm.
So the example that Kevin is showing is a really small system on the molecular side, where there are just few orbitals. As you will go to heavier system, it will become more and more continuous. Please.
What is your band gap in your density of states? And how do you know if that's the right band
More
gap
correct, what's the band gap of the model?
for the model?
I don't remember what the specific band gap is for this.
Okay.
Ask Kweeni. He gave us a lecture on what is band gap. Yes.
Yeah.
So, and Kweeni, what is the gap on this image that Kevin is showing?
Well, you have to go back to the function used.
Just roughly.
It's about -15.
15.
Well, 15,
Around
15.
10.
I would say 13.
13. 13.
Okay. So you just measure offset from occupied to unoccupied, right?
How'd you get the 1 and 2?
You actually answered my question.
Okay.
So,
Sorry.
I need to leave.
I didn't actually make this.
Oh, you didn't make that one? So
No.
what's the 1 and 2 correspond to? They correspond to something special, right?
I'm not really sure.
Columns.
Based on your previous lines, it's likely getting hydroxide.
All right.
So really small, power 9 atom model. More questions? If no, let's thank Kevin and Sudipto Saha is the next presenter, and we need to finish 3 presentations in 20 minutes.
Okay.
There are two aspects of continuity. First, if there is a lots of levels, and second, we artificially add body that will make it continuous even if they are sparse.
Okay, so after so many hard topics, maybe I am going to present the easiest one. So I am basically going to present gnuplot software and how to use that for plotting different numerical data. So what is the gnuplot software? This software is quite useful one. I found this software super useful for me and for my research. Maybe you guys will also find it super useful. And this one is free, the most important thing, and it can do both interactive and batch modes. So batch mode of operation. So this one is quite user friendly. I found it user friendly. So in this software, how we usually plot data. So what we can do, sir? Suppose I'm trying to plot a function. Suppose my function is like f of x is equal to e to the power minus x squared divided by 2. By the way, in this software, it cannot consider that power sign. So if you want to make a power sign, you will have to put double star. So in this way, it usually considers power. So suppose this is my function and I want to plot it. So the command I will give in the software, like just plot, and suppose in my x-axis I want to make make the variables name not x, it should be t. So I am setting the variables name t for -4 to 4 and then f of t. Then it will plot my function. And if I want to plot another function on the same graph, then I will just add another function like t squared divided by 16. Then it will plot both the function in the same curve. And suppose I'm done with plotting the software, plotting the curves or the main function. Like this is the preliminary step. I want to plot one function, or I want to plot 2 functions at a time. Now I want to set some labels, set x levels, y levels, or titles. These things are pretty simple one. I can give commands like set title, set x level, set y level. And if I want to see the grids, I can use set grid. And after giving this command, I want to plot it again, just replot. And before replot, you can command like reset, and then it will remove the previous curve and it will replot. So this is how we can plot a function. But if we have some data, like usually we deal with data, we have a couple of data that we want to plot, like density of state, or there are many other ways, like I want to plot EK curve or many other things we want to plot. So how we can plot data? So before to plot a data, you will have to write all the data in one text file, and then like there
in that text file there may be several columns, like one column for independent variables and the second or third or fourth columns, those can be of dependent variables, and you can choose which column you want to use. So, and there should be no you can add comments with that sign. You cannot see it here, but it's in the slide, so you can use that this sign. So you can add comments with this sign. I don't know the name of this sign.
Hashtag.
Hashtag. Thank you. So, and if you and each of the fields should be separated by a tab. And so after entering the data into a text file, you can plot it. How you can plot it? Just this one is pretty simple one. Like you will just give a command like plot my file name dot data or whatever dot txt, and you can set the title, like title name, what you want to give as the title. And like it is pretty common that we want to consider the uncertainties in the dependent variable, and we can set it with the y error bars. And if we set it with y error bars, then it will consider the uncertainty of the dependent variable with respect to the independent variables. And we can also include x errors by x error bars, or both x and y axis errors with x or error bars. And this is another very useful tool while using this gnuplot software, that is using. Suppose I have a curve, I have a text file with 3 or 4 columns, and in that curve, like in that file, the first column is of I want to make it dependent variable, or I want to make it a y-axis, and the second column I want to make it my x-axis. So how we can do that? Like just plot that file name using 2:1. This 2:1 means it will make the second column as your independent variable, like x-axis, and the first column as your dependent variable, like y-axis. And suppose I want to plot, like I have 3 columns and I want to plot 2 curves at a time. Well, first one is like keeping the independent variable in x-axis. One curve should be 1:2, and the second curve should be 1:3. Then things are pretty simple. Like I am just giving one command, like plot double dot data, whatever the file name, using 1:2, and I am making the title that this is series 1. And then another comment with a comma, I can give another comment like double data using 1:3. So if we see a curve here, so it should, I made a file for myself just to see what happens here. So with that command, I have found that this is 1:2 for this one, and 1:3 for this one. So in this way, we can plot several data in one curve, and if we want to plot different data in different curves, we can use that using function, and we can subplot at a time. So these things are pretty simple. And suppose you cannot see it here. So the column is basically mentioned by this $sign. So $1 means first column, $2 means second column, $3 means third column. So if you want to modify it, kind of, you can give a comment like plot whatever it is, the file name, using 1:2 log $2. So it will take the logarithm of second column, and then it will plot it against first column. So these are the pretty useful tools, and there are many other comments we can, like whatever we want, we can just search online. And I am just giving a brief introduction to this software, that these are the things, and if you want, you can search online what command you need for your purpose. So if we want to use this software for plotting density of states, we can easily do that. Like first, first of all, we will have to rename the DOS data file as dos.log and making it a log file. Then we can it can be downloaded to plot on Excel also. And then we are calling the gnuplot software, and we are calling the script to plot the DOS data. So it's on that comment. And here in this line, what we are doing, like set term post line width, we are setting the line width 4, and we are setting the font as Helvetica, and we are setting all these things like X levels, Y levels, and then we are giving a comment like plot dos.log. And U means basically using, and 1:2 means x-axis and y-axis with line. If we use WP, then it will not create any line, it will rather create points, and it will not add those points. So if we want to add the points, then we will use with line. And if we want to see these things as a PDF form, or we can convert the PS file to a PDF file using this command, and we can also download this PDF file for our purpose. And here I have created the density of state function for H2O, and I cannot measure the band gap, but this one is the conduction band, this one is the valence band, the gap
Opposite.
Oh, sorry. This one is the valence band, this one is the conduction band, and the gap between the conduction band and valence band should be the band gap. So we have plotted that using the GNU software. So in conclusion, I can say that I found this software really very helpful, which can be used for plotting the different types of 2D or 3D curves. And gnuplot software, it's really easy to use, and I found it useful. So thank you.
Thank you.
Sure.
Kweeni and then Kevin.
Yep.
Do you have free software?
Yeah, that's the most interesting thing. This is a free
GNU
software.
means free. GNU, any software that starts with GNU.
Yep.
Kevin?
Can you go back to the second to last slide?
This one?
Yeah, that one. All right, so that huge space in the middle, where from -10 to 0 to where that first line began, that's the band gap. And you said to the right hand side of that is conduction or valence.
Conduction.
Okay, and to the left is valence.
Valence.
Okay.
Kevin? So in all books right now the terminology changes, but there were like 3 bands: conduction band, valence band, and forbidden band. Like what we call band gap is forbidden band because there are no states there.
Okay.
Like in China, forbidden city.
All right.
More questions to Sudipto?
I have one more question.
Sure.
So instead of using like G and uplot, why can't I just export all of my data and just like make a graph in Excel? Why is this better than like using Excel to plot?
Sorry.
Why is G and uplot better than using Excel?
Good question.
It's quicker.
Okay.
You can do this all the time.
Like usually, I found that in different literature papers they use this type of softwares, not the Excel graph.
Okay.
Excel's, I don't think it's you're gonna have to import
Maybe
it, you
ex-
have to export the data. This one you just put do, and you're done.
Okay.
You can produce the data.
Yep.
More questions? If not, thanks Sudipto once again. And David and me will show us how to make 2 presentations in 8 minutes. So, if I would be taking this class, I would select the same subject as David because it is.
That's
shows
why David
orbitals.
picked first. So I'm going to show you how to make or plot molecular orbitals. So the first step in the process is to convert your checkpoint file that you get all when you run a Gaussian into the formatted checkpoint file, and you do that with the form check command. So you type in your command and type the file you're going to convert, and then the file name you want it to become. So you also, at this point, you need to choose the orbitals you want to pick. So this is the same file that Kweeni showed us earlier, and I have highlighted here, you can't see the occupancy, but I have the HOMO and the LUMO circled here. So if it has a 2, it's occupied, and where it switches from 2 to 0 is the HOMO LUMO. And I also showed over here from the log file where you can see that, so it switches from occupied to virtual. So if you were to count all these up, you could find out what your HOMO orbital is. So then you need to generate a cube file from the formatted checkpoint file. And we do that with the CubeGen command. So if you notice here, I made files for the HOMO and the HOMO -1 orbitals. And you type CubeGen, the O, then your molecular orbital number, the formatted checkpoint file, and your output file. And the area that I have boxed here in red, there are several different options you can use. So what I have here is MO equals N, which lets us specify which specific molecular orbital we're looking at. You could also use AMO and EMO equals N. Those will select the alpha or beta spin occupancy orbitals. So then to actually make your molecular orbital, you need to come into Gauss view, you go to results, you go to surface and contours here, and that'll open up this window. From here you go to surface actions and click new surface, and it'll give you a molecular orbital diagram like this. And there are a few options down here that you can change to adjust how it looks, like the ISO value here. And that'll just change the size of the clouds. So then the other thing to look at here is the open shell configuration. So that indicates that we have unpaired electrons. So I'm using Hexa Aqua Titanium 3 here, which has an electron configuration of argon 3D1. So if you go into our input file that I want to say Nathan was looking at, you can see that my multiplicity is a doublet here. So that's going to give us our alpha and our beta orbitals. So then just like we did here, we make CubeGen, except here we would use AMO and BMO to find it. And then when you actually plot them, they will have differences. So these are orientated in the same frame of reference. And you have your alpha molecular orbital and your beta molecular orbital.
So it's the same number of orbitals.
So in this case, the beta was orbital 34, the alpha was orbital 35. If I remember. And it's covered up, but I'm pretty sure it was 34 and 35.
Oh, it's HOMO.
Yes, this is the HOMO.
HOMO of beta is p orbital of oxygen, and HOMO of alpha is d orbital.
Yeah.
Okay, makes sense. Is it the last one?
Yep.
Thanks. Any quick questions while he is turning back? If no, then thank you once again. And there will be our champion.
Coach.
Change
Probably.
presentation.
Change PowerPoints though.
Change PowerPoint. Meade will show how to do presentation in 2 minutes or 1 minute and 30 seconds.
Well, luckily it's pretty quick. A lot of this information that people have provided to today kind of helps set up where I'm at. So electrostatic potential, Mulliken charge, and isosurfaces. Just earlier, comment that David had just said, form check files. Earlier, I believe Anas had gone over how to calculate, optimize. And in our case, we did in my case, I did DFT and then LSDA. You guys should be able to see it on your sheet of paper. So this is for the electrostatic potential. We talked about some coding we were using. We need CubeGen files or fcheck we need cube files. We can get that with fcheck and cube generation. And I have the code written on here so you guys can use it for later. And this is supposed to be the values we get once we go to the results. Click surfaces contours, and you'll be wanting to click on, right here. And once that comes up, you have this information. You do press OK, and this value comes up. I tried changing some of these values, and they were supposed to change the figure, but they never did. So I don't know if my situation had issues or not. And then this is the Mulliken charge visualization. All it does is tell you the charge. Green is positive, red is negative. Easy. Once again, we go to results again. This is where all our information comes from. That's why we calculated stuff earlier. And I love the smiley, just for you, Kevin. And we want to make sure we go to click charge distribution in the results section and uncheck these. So I believe one of them is checked and the two usually aren't, but just make sure they aren't. Okay. You can change formatting as well. And then this for ISO services, we had done this. We need log files, and I do want to kind of show that I want to know what the ISO surface tells you, what value through the contour surface, but I don't know what I was looking at. If it was like electronegativity or magnetism of some sort, I apologize. And then so happened to look like Zoidberg, so I put that on. So that's it.
Okay, let's thank him. And let me suggest to ask him questions by email because we are running out of time, and some of you have responsibilities, drives, and
dinner.
And dinner, yes. So many thanks to all presenters. This session will be available online, hopefully, and
looking forward to see you tomorrow at 5, same place.